Hi, this is Dave Erickson. Welcome to Erickson Engineering, my electronics website. Went over a friend's house recently and he had this old HP multimeter. It's a 3466A and didn't work. And I thought, okay, I'll bring it home, see if I can fix it. And I didn't know much about it, but it turns out it's a pretty classy multimeter. It's 4.5 digits. It has a battery option. In fact, the first thing I noticed when I picked it up was, this thing weighs about 3 pounds. And I thought, it's kind of heavy for a plastic multimeter, but it turns out there's a big old battery in there. It has a fairly wide range of ranges. Notice the millivolts go all the way from 20 millivolts to 2,000 volts. I'm not sure I'd want to apply 2,000 volts to this, but at least 1,200. That 20 millivolt range is pretty high performance. But it turns out in current, it also goes down to 200 microamps. And that's pretty nice. At 4.5 digits, that resolves down to what's that, 10 nanoamps? So yeah, this is a pretty nice meter. In fact, it resolves in current down below what my 34401, my high-end meters work at. Anyway, it's a pretty high performance. However, it had some problems. One of the problems is this. It always displays overload. When I first got it, it didn't display ohms at all. It just displayed overload and then a digit, and the digit was kind of random. So I didn't know what kind of battery was in there, and the battery certainly didn't work. So when you unplug the unit, the display goes out instantly. So there's no indication of battery. And it's interesting that this unit doesn't have no battery indicators, no standby power switch, no nothing. You just plug it in and turn it on. And it's supposed to operate off battery. So I opened it up and took a look inside to see what was going on. I'll show you how to take it apart. I've had it apart before. It's fairly simple to take apart. So let's unplug it. And put the handle in the middle. And if you look at the bottom, there's 4 long screws that hold it together. And I think I've got a couple of them out already. So it should be pretty quick. Oh no, they're all in. So once you get the 4 screws out, they kind of fall out. Then you remove the top. Which is unreasonably heavy. And you discover why it's so heavy. And it just folds aside. Of course, the reason it's heavy is because there's the battery mounted to the top. So here's the inside. So to remove the electronics, you can do a fair amount here. You can measure the power supply, without taking it any further apart. There's 2 boards and a pretty comprehensive shield between them. So you can see the power supply section. You can see some of the circuitry on the analog board. The top board is a digital board with a controller chip on it, and you can access things, but you can't do much. For example, you can't resolder. You can't do any soldering work on the top board unless you remove the front panel. The front panel plugs into the top board. So in order to get the digital board, you have to remove the front panel, but that's fairly straightforward. And there's 3 screws. There's one semi-buried over here that you have to remove, and you also have to remove these 2 that are on the transformer, plus this one. Remove those screws, and then the whole electronics assembly lifts out. So I've got the screws out, and now I can lift the whole assembly out. It's a little. Got to wiggle it a little bit, and there's all the electronics. So now I can move the case aside. Oh, I also disconnected the power cable from the battery assembly. Which, by the way, the battery on this is an option. So this whole top assembly and all the weight and battery associated with it is an option. To take it further apart, there's 2 screws here that hold down the main board, and they also clamp the shield to the bottom board. So everything is sort of held together by those screws. Then when you remove after you remove those two screws, but before you do that, the front panel just pops off. There are no screws holding it in. You can see there's a connector, there's these two wires, and then there's a zeroing trim pot which goes through the front panel. But yeah, the front panel just pops off like that. Oh, also there's a fuse, which is the 2 amp current range fuse. That's on the current range. So yeah, that's sort of just sitting there. So that's the whole assembly. Like I say, 2 screws. Remove those. And the whole piece digital board just pops right out. So that's fairly easy to disassemble. And then the next step is, notice there's 3 screws, 1, 2, 3, that hold the shield on. So if you have to go further, 1, 2, 3, and you can see there's some documentation here. Tells you how to configure it for AC, the usual warnings, and also where all the trim pots are for calibration. So you shouldn't, if all you have to do is calibrate, you shouldn't have to take this apart any further. In fact, you don't even have to take the digital board out. So here's a quick tour of the main board. You can see the AC inlet up in the upper right corner, the filter capacitors, and the transformer. At first I thought, how does this thing work? It doesn't have a standby switch. It only has a 1 on switch. And it turns out the power, the raw power, you know, the transformers and the filter capacitors and the rectifiers are on all the time. And when you hit the power switch, which is way down here, you know, in the lower left, it enables all the power supply voltages, the 7 volts and the -7 volts and all the references, which is an interesting design. I think they do that so that there's power available to charge the batteries all the time. So if you there's no standby LED, no power, no battery LED. The thing just works, and when the battery runs low, it gives you an indication that you need to charge it. The other thing about this instrument, which I found interesting, is on the inside of the case. Let's see if I can find it here. Oh yeah. On the actual battery itself, there's a warning. This is the battery and the battery charge circuit. This is an old NiCad battery. This thing was designed in the 70s. It says for maximum battery life, keep multimeter connected to power line whenever possible. It turns out if you don't, then the battery will self-discharge over time. So, and of course my buddy had it sitting in this garage for many years unplugged, so the battery's dead, of course. It has enough power to maybe run the thing for a few minutes, but that's it. So yeah, at some point I'll replace it. I'm thinking maybe I can replace it with nickel metal hydrides, but whatever. If I can't, I'll go get some NiCad batteries and take the battery package apart and replace the cells in it. So yeah, on the input you can obviously see all the switches. The switches, here's the front panel. The function switches on the left, the range switches are on the right. It does have auto ranging. The AC switch is the far the AC power switch is the far left one. And at first I was worried that they ran AC power all the way on the board from down to the left, but it turns out it's just a DC switch. And so there's no risk. So as long as you stay away from the upper right hand corner of the board, it's reasonably safe to work on. Everything else is low voltage. So from the input, you can see the red and black wires coming from the input jacks, and they wire directly into the switching. There's the input relay, which there's only one relay on this design, and it switches high and low voltage. So it's, I guess they needed a relay to switch the 220 millivolt ranges. The next device up is the input hybrid, and that's interesting. It's obviously proprietary, and it has a nice socketed package. I don't think I can get enough detail. But these pins are spring-loaded gold contacts. And what you can't see here, you can sort of see it up here on this next device. Probably 6 or 8 of the pins of this device are run through. You can sort of see it on the lower right. It's a little tricky to see down here. But instead of going directly to the circuit board, they go to Teflon standoffs, Teflon feed-throughs. And they use Teflon feed-throughs quite a bit on this board. I'll show you the back of the board and you'll see how many Teflon feed-throughs. Yeah, you can see in that input section over there, there's 4 Teflon feed-throughs, the red and black ones. So yeah, that big black device is the input, is the relay for the low voltage switching. That FET right there, that metal package, oops, that's the limit of my zoom. The metal package there is a dual FET for the input, and that works in conjunction with an op amp. Going up, the next device, also proprietary hybrid, is the integrator hybrid, and that controls the integrator. And on the left, upper left, you see the op amp. That's the integrator, and the Teflon capacitor. This big Teflon capacitor, that's the integrating capacitor. Next up is the RMS to DC, and I'm pretty sure that's an analog devices part. It has a proprietary part number like everything on this board. Next up is these 2 ICs, and I'm pretty sure that's where the problem with this device is. Those 2 ICs form a comparator. So the output of the integrator gets compared to ground, and if it's above or below, they close the loop on it, and that's what the dual slope A to D. That's how the dual slope A to D works. And those are proprietary numbers, of course, just like everything. They're 16-pin devices, and they're shown on the schematic in pretty good detail. And it turns out each one is 5 transistors. There's 3 NPN transistors and 2 PNP transistors. So the total comparator consists of 10 transistors. It's a circuit consisting of 10 transistors. And those resistors and capacitors and diodes that you see are the rest of the comparator circuit. And I'm 90% sure that it's dead. I'm sorry, 99% sure that it's dead, and I'm 90% sure that when I fix it, then the functionality of the meter will come back. Because what happens is, if the comparator is stuck high or stuck low, which it is, if the output is stuck high, then it can't control the feedback loop, and it fails immediately. Can't auto zero, can't do any of its standard functions. Everything fails. So yeah, I'm pretty sure that's the second problem. This is an LM339 that I replaced. Its job is a level shifter between the 7-volt logic coming from the controller. It controls one of the input gain FETs, also for the low voltage range. And the circuit, let me grab the circuit for you. Okay, here's the circuit down here. So those 2 signals, J10, the 2 input signals, are just 2 outputs from a flip-flop, and they're the Q and Q bar output, so they're complementary. And this circuit is a level shifter whose job it is to convert the 7-volt logic. You can see the threshold is set by these 2 resistors at right halfway to 7 volts, so 3.5 volt threshold. The outputs are either pulled negative to -7 volts by the comparators, they're open drain, or they float high, in which case they go to ground. And notice they control 2 JFETs, and those are in depletion mode, standard depletion mode JFETs. And one of them sets the input of the input amplifier to ground. The other one sets the input of the input amplifier to this circuit up here, which, by the way, is where the relay is. So yeah, I checked the voltages on pin 1 and pin 2 of that device, and they were both ground. And I thought, that's not right. There's no way this circuit should ever, since the inputs are complementary, and sure enough, the inputs were complementary and the outputs were dead. So anyway, I replaced that device. I got all excited. I found the problem. Yay, this is great. I'm going to fix this thing. And so I socketed the IC. Anyway, I had an ancient LM339 in my stock, plugged it in, and sure enough, that circuit worked, but I still get the overload output. Troubleshooting is switching between elation and despair. So I was elated when I found the problem and fixed it, and then I was despaired again when I realized, no, that's not the problem. This thing has bigger issues. And of course, if the proprietary chips, there's 3 proprietary chips on this system. There's the 2 hybrids shown here, and here I'll show you the controller board. And here's the controller board, and that big white 40-pin dip in the middle, that's the main controller, and that's also a proprietary device. So sure enough, if any of those parts are bad, then the instrument is probably toast. But yeah, I'm pretty happy with the instrument. It seems like a good quality one. It does some really good things. So I figured it's worth fixing. So let's look at the controller board again. You can see the large headers in the middle, those big strip headers. And if you flip it upside down, you'll see these gold pins. Those are the digital control signals that go between the control board and the main board. This connector over here drives the LED, and in fact there's an offset pot, and it's my favorite old CTS potentiometer. If you're not familiar with these are multi-turn pots where the balls in the back form a planetary drive, and it gives you a poor man's 10-turn potentiometer, and that's used for offset, and that goes to the offset adjust, which is right on the front panel. The stuff on the right is mostly the LED drivers and the front panel drivers, and the stuff on the left is the timing and control. The crystal, I've heard other people say, check the crystal. The unit was operating extra fast, and it turned out the crystal was broken. It turns out it's a 200 kilohertz crystal, which is very low. And these things are kind of delicate, so if the instrument has ever been dropped, there's a chance that the crystal will break. There's not any particular cushioning for that crystal. It's only 200 kilohertz, and I thought, 200 kilohertz, that's a very low frequency. But it turns out that these timing circuits on the left divide it by 20, and the controller only operates at 10 kilohertz. So the clock for the controller is only 10 kilohertz, which I thought was pretty interesting. That was my first hint that this was not a microprocessor, that this was a custom controller chip. The second hint was that everything is 7-volt logic. It's like, oh yeah, I use that standard 7-volt logic. This logic was all fine. So now I'll give you a hint of the problem. Notice that the logic chips, these are all 4000 series CMOS. Again, proprietary HP numbers. Notice that they're all National or Motorola. National Semiconductor or Motorola. It's like, okay, good. National Semiconductor and Motorola, that's good. And it turns out, the comparator that blew out was also a National chip. So after I fixed the comparator and it didn't repair the problem, I went to sleep and woke up the next morning. Of course, I'm obsessed with this thing, so this is all I do for the next couple of days, is to try to get this thing fixed. And I thought, you know, if the 20-cent quad comparator is broken, maybe the 20-cent the resistor networks in the A to D comparator are also bad. And I thought about it for about 10 minutes, and I realized, oh wait, these are just transistors in here. If they are bad, I may be able to replace them with discrete transistors for now, or maybe I can find the device. So originally I thought, a transistor array. The standard transistor array of the 70s was the CA3046, which was made by RCA. And it turns out these are still RCA parts. So that was another hint. But I started looking at the pinout of the CA3046 and realized, no, these are 16 pins, not 14 pins. The CA36 is a 14 pin. So I started investigating. Fortunately, you can look up HP part numbers and find substitutes online. So I looked up the part number and found out that it's not a 3046, it's a CA3096, which is another uncommitted transistor array. Has 5 transistors, 3 NPNs and 2 PNPs. So it's a pretty useful part. And those 10 transistors are used to make the comparator. It's a high-speed comparator, so it has to operate fairly accurately and fairly high speed. And there probably wasn't an off-the-shelf part that was anywhere near as cheap as this. It uses a fair number of discrete components as well. So yeah, since it's just transistors, you put your multimeter in the diode range, and the very first transistor I measured shows up bad. Put the multimeter in the diode range. So the first transistor in the circuit is the base is on pin 1 of this guy, and that's the input of the comparator. So I thought, no, that's a good place to start. Start there. So I measured the base to emitter, and I get 0.8 volts. It's like, 0.8, that's a little high. Usually it should be 0.7 or less. And then I measured the base to collector, and I get 1.4 volts, and that's way off. So sure enough, the first transistor is dead. So I measured a couple more transistors in there, and turns out there's 3 or 4 transistors that are dead in that device. My plan is to remove those devices because they're not doing any good, dead like they are, and socket them, put in IC sockets, and then maybe if I'm lucky, I can just throw in some 2N3906s and 2N3904s to at least get the thing working, and then go out and order the CA3096s. CA3096s are not that readily available. You can buy them on Amazon, but most of them are being shipped from China. So I did a little blow up of the integrator and comparator circuit, and you can see the integrator on the left with its integrating capacitor, and there's the comparator. It's made of discrete transistors. This first stage is differential pair, inverting amplifier, and output buffer, and then this is the feedback resistor, and that's the input. So this is a configuration is a non-inverting gain of 100. So 49.9K divided by 499 ohms is a factor of 100. So the first stage is high gain, and there's a little compensation capacitor on it. Second stage, the polarity's flipped. So notice on the first stage the +7 is on the top and the -7 is on the bottom, as it should be. And the second stage is all inverted. So this is an NPN pair. This is a PNP pair over here. So it's the same kind of amplifier, same kind of buffer, except it has an output diode. And this is a gain of let's see, what's that? 12.5K over 500 ohms. So a gain of about 25. So the overall total gain is about 2,500. And then the output stage is just a differential pair, and then that's the output is off the collector. So it's either going to be probably 0 or 7 volts, depending on whether this input is high or low. So yeah, it's just a high gain amplifier designed to deal with saturation. Obviously the thing's going to saturate like crazy because the input voltage can vary up to a couple of volts. So yeah, that's the stage. Now the question is, can I get this thing to function if I just replace the transistors? So here's the data sheet for a CA3096, 2 PNPs and 3 NPNs in it. And here's the pinout for it, a little markup. Notice that those are the top views of some TO92 transistors. So if I just put a proper IC socket in there, I should be able to just plug transistors directly in. Notice that the PNPs on the right, I'll just use 2N3906s, and they just plug directly in if I spread the leads a little bit. The one on the bottom is an NPN. The three on the left are all NPN, so I'll use two N3904s. The middle one is easy to plug in. The other ones I'll have to monkey with the leads a little bit to get them to plug in. But yeah, that seems like a reasonable plan. If this fixes the problem, or if it at least gets the instrument working, then it's worth for me to order those parts, wait for them to come in and replace them. If it doesn't do it, then I'll have to dig more. And again, I'm hoping that the proprietary hybrids are not and ICs are not bad. Because if they are, then this instrument is pretty much toast. Powered up the solder sucker and see if I can't remove these without doing too much damage to the board. And like I say, I'll socket them once they're out. Well, that's most of the solder. We'll turn it over and clean it up. And with a little care and patience, I was able to get them out without too much problem. Here's the two devices that came out off the board. Now I can measure the transistors again out of circuit, and I'm sure I'll see similar results. Looking pretty good. So I'll touch up the solder on that, clean it off, and put some proper machine contact sockets in there. So I have a bunch of 14-pin machine contact sockets, but only one 16-pin left over. So I try to use machine contact sockets wherever I can. Here's my home-brewed CA3096s. Made out of NPN and PNP transistors and some judicious lead bending. Three of the transistors just dropped right in, then two of them required a little bit of special operations on the leads, but so far so good. So let's power this thing up and cross your fingers. Put it back together first. So the way I do this on the bench is first you plug in the controller board, making sure the pins line up, and notice how long the pins are on this thing. Make sure none of them are bent. It would be really easy for one of them to not plug in correctly. That takes a little care. Then I usually hang it off the front of the bench like this and install the front panel, dressing the leads correctly. Start by getting the switches lined up, which is easier said than done. Line up the connector, plug it in, check my work. There we go. And plug in the AC cord. And oh my god, it's working. Apply a voltage here. 1 volt. Oh my goodness, look at that. And it reads a volt. It's fantastic. Fantastic. Currently hooked to my source measure unit as a voltage source, which is undergoing development, but you know, it still works. 0 volts. I'm on the 2 volt range here. 1 volt, 1.5. So I'm outputting 1.5. Let's put the source meter into the 15 volt range. It should overload. By the way, it would only read overload 6, 7, 8, 9, and it would just stay stuck forever. So I wasn't sure what I know what the OL means, that means overload, but I wasn't sure what that last digit meant. When it was failing, it would just read overload and it would sit there stuck forever. So here we are on the 15 volt range, so let me put this on 20. And there's 15 volts, 7 volts, 2 volts, 0 volts, -8, -15, yay! And then let's move up to the 200 volt range. Put the source meter on the 150 volt range, should be 70 volts out. 50, -50 volts, -150, so it's not, oh, notice that we are missing a digit. So it went from a 4.5 digit meter to a 3.5 digit meter. So I have to figure out what's up with that. I'm hoping it's just a driver transistor, although I might have some of those LEDs left over from a previous project. But yeah, it's working. At least it's working in volts. I haven't tested it in the other ranges yet, but at least now it's worth fixing. It's worth replacing those ICs, ordering them, fixing the battery, blah blah blah. If I couldn't get the meter working, if one of those hybrids was bad, then it would be pointless to put more effort into it. But now it looks like it is worth some effort. So I'm excited about that. So I thought I'd take a look at troubleshooting the LED driver problem. So this is the controller board schematic. Over on the left we have the controller IC. This guy right here is the flip-flop that outputs the two complementary signals that switch the low voltage FETs. That comparator that I fixed. I fixed two comparators. The first comparator, which was the level shifter for driving two JFETs. So that's how I knew that the signals were complementary, because they're just coming off a flip-flop, Q and Q bar. This is the clock oscillator up here. You can see the 200 kilohertz crystal, which goes into a divider, which then goes into a, I think it's just a 7-segment, yeah. So that goes into a 7-segment decoder. So let's see if we can't figure out what's up with the missing digit. It should be set for 100 volts and it's reading 99, but no, and it's on the 1000 volt range right now. There's a missing digit there. So the soldering was pretty ugly on that device. It looked like it had been replaced at least once before. And there was a fair amount of flux on the board, and I thought, well, I'll clean it up. So I took off the old solder, cleaned up the flux, applied some new solder, and let's see how it goes. And sure enough, 7, 8, 9 seconds into operation, out goes digit 4. Okay, go fish. So next I'm going to see if the LED itself is bad, because that's probably the next most likely thing. So I probably need to replace that LED. So I was able to get the fourth digit working. Here it is operating from the source measure unit, 18, 19, 20. And the calibration is, you know, it's within a fair couple of counts. It's pretty good. The auto ranging is working on the meter, which is great. 30 volts. Turn it down to 13 and get that extra digit. So yeah, I'm pretty happy with this. So let me explain what was wrong with that last digit. Here's the schematic, and there's the 3.5 digits. And if you notice, these 3 digits come off of these resistors here, which are just driven from Darlington drivers, which come off the control chip. But the fourth digit has a separate bus, and it's driven off of these Darlington drivers with separate resistors. And it's interesting. The resistor values are different because the 3.5 digits are all multiplexed, so they're only operating at, you know, maybe I think a quarter of the current, and so those are using 220 ohm resistors, whereas the fourth digit is operating statically, which means that it's not multiplexed, so it's driven 100% of the time, and so that's using 1K resistors, and the current through the LED is about 5 milliamps. The power supply for the LEDs is this thing called display power up here. You can see it just comes in for this fourth digit is just coming in off a inductor and capacitor. So just a simple filter, about 6.3 volts. So why is that digit blanking? At first I thought it was the LED digit, so I pulled it out. I was going to replace it, but I tested it outside and it was working fine. It was weird that it was intermittent. You know, the problem would appear somewhere between 5 and 15 seconds after you first power the unit up. Can't be this driver because this is two different chips, so that would affect some segments, but not all the segments. And the same with the decimal point. And then the next chip back is this guy. It's a CD4511, which is a 7-segment decoder, but it also contains a latch. And then the next chip back is a counter, an MC14518. And I remember that counter from my early days of designing. That's a dual decade counter. And notice that that comes right off the clock, the 200 kilohertz clock of the system. So what's going on there? I think what's happening is the controller chip is designed for a 3.5 digit multimeter. And in order to add the fourth digit, they had to add an additional counter and additional 7-segment display. If you think about it, it's kind of crazy. And that's this logic here. So I looked at the chip, the CD4511. I looked at the data sheet for that. It has a pin right here, pin 4, which is an enable. When you drive pin 4 low, the digit blanks. I'm like, okay, that's weird. So I look at this logic here and notice there's a flip-flop, a CD4013, driven by some crazy combinatorial logic of pull-up resistors and open drain inverters. It's like, what's going on there? And sure enough, I checked. So the clock and the data pin were fine, but the output would go low intermittently. And so I said, okay, it's got to be this 4013 chip, U903. And sure enough, I replaced U903 with another device. Unit came back to life, and the fourth digit came on. So what are we up to? 4 devices now, right? All pretty much jelly bean parts. 1 quad comparator, 1 dual flip-flop, this guy, and the 2 transistor arrays. Been using it for about 24 hours now, and no problems. Everything seems to be working fine on it. So that's kind of exciting. There's the U903, this guy here. I pulled the unit out. I figured the IC must be intermittent. I probed around on it and I couldn't get it to fail or work. It seemed like a strange intermittent, because these things use almost no power, these 4000 series logic. So anyway, I pulled it out, put a socket in, put in a new chip, which I happen to have in my stock, and presto, the unit's working. So that's kind of exciting. So I'll put it all back together, put the shields, install the shields, maybe do some a little bit better calibration on it. But I'll check the calibration on all the ranges. So if you notice, there's a battery connector here, and here's the battery. Here's the connector from the charger board. It's the same battery connector. But this has the one on the board has a red jumper, and I've added that red jumper myself. If you don't plug in the battery cable from the battery, then you need this red jumper to bypass the power. So anyway, that's been plugged in, and I've been doing all my debug with the red jumper in place. But I'm about to remove the red jumper and install the battery pack and see if I can get the battery pack working. I think what I'm going to try to do, it says that the battery pack is 7.2 volts. So I suspect that it might be 6. It says charge it at 7.2. So I don't know how many batteries there are in there. I'm going to guess 5, the equivalent of 5 NiCads. But I'll have to take the battery pack apart and see what's actually in there. I'm hoping I can replace them with nickel metal hydrides because they're easy to use, and I have a bunch of nickel metal hydrides around, left over from the good old days of batteries. Yeah, we'll see if I can't adapt this to nickel metal hydrides. If not, I can save about 1.5 pounds of weight on this meter by just removing the whole battery assembly and using it as a benchtop instrument. Although it seems like it would be useful to have it operate off batteries. We'll see. So I removed the red jumper wire and plugged the battery pack back in. As soon as you unplug the power, the battery voltage drops from 7.2 volts to 1 volt in about a second. So yeah, that battery is, as suspected, it's dead. I charged it overnight. It has 7.2 volts on it, so I think the charger circuit's working. But the battery itself just isn't holding any charge at all. You can see I have it unplugged. What I did was temporarily hooked up my power supply, set for 7.5 volts, and you can see the current is about a 1/4 amp. So that's what the meter draws off the battery. So it looks like off of a 200 amp hour battery, you'll probably get 10 hours on the battery. I don't know what this battery is designed for. And let's see what happens if I drop the voltage to 6.5 volts. Current actually drops down. So it looks like they're not using any switchers, they're just using a linear supply off the battery. But the unit is still working. Let's see where it drops out. 6.5. Oh, and there it goes. So somewhere around 5.5, 6 volts, the unit shuts down. So it needs at least 6 volts. Could it be 5 cells? I don't know. It's either 5 or 6. So I'll take the battery pack apart, count the number of cells that are in it. So that's next. So removing the battery pack is pretty straightforward. I removed these 2 screws here, and the board and the battery both lift out. So there's the charger board, and there's the battery pack. And it looks like a fairly standard Gates. Oh, look at that! I guessed wrong. This is not a NiCad. This is a Gates sealed lead acid battery. I don't know why I didn't think that. Anyway, it's a 6 volt, pretty standard sealed lead acid. So I should be able to get. You can see the cells through the holes in the top. I should be able to get some of those cells, possibly even buy this unit. It's got a part number on it. So see what we can do. Well, thanks for watching part 1 of this video on repairing the HP3466A meter. On part 2, I'm going to see about replacing the old lead acid batteries with some modern lithium batteries and see how that works. Thanks a lot. Don't forget to check if you like this video, and subscribe if you like to see more videos like this. Thank you so much.